Hi, this is section 1.8 on molecular orbital theory. Your book has a nice discussion on it, so I'd recommend you have a look at that. What I'm going to do is give you an idea of this chapter in my words to try and help you as you read this for yourself. So let's go to the notebook so we can discuss this a little bit. Oh, I don't have the notebook open. Okay, so we're going to be talking about molecular orbital theory, which has a very different approach to talking about bonding than does valence bond theory. So if you remember in valence bond theory, the focus was completely on the constructive and destructive interference of electrons as waves. However, now we're going to be talking about bonding in terms of the mathematical nature of quantum mechanics. So what does that mean? So first, when we're talking about this, let's make a little energy diagram to make it easier to understand. So in this energy diagram, energy is always increasing, going up. So let's make a bond between, I don't know, let's say the chlorine 2p, the 2p orbital here, and let's say a hydrogen 1s orbital. Okay, and I'm actually going to move this over a little bit so we have some room. All right, so in molecular orbital theory, it says that we are going to take two atomic orbitals, such as the ones that we just drew. Those orbitals are going to have electrons in them, like so. And we're going to mix these orbitals together to make a bonding interaction. So by mixing these together, that means we're going to create one that's lower energy, a new orbital, that is, and a new orbital that's higher energy. These are called molecular orbitals, and we're building them by doing a linear combination of both of these atomic orbitals that we're talking about right now. And in fact, if this were to be truthful, the 1s orbital is in much lower energy, so it should probably be down here. Which means this energy level should also move probably down there. There we are. Okay. Now with these two molecular orbitals, now we're in a situation to where we need to fill them with the electrons from our atomic orbitals. Because remember, we started with atomic orbitals and now we're using molecular orbitals. So using the Aufbau principle, the Pauli exclusion principle, and Hund's rule, we remembered that we need to add electrons to the lowest energy level, filling all degenerate levels first, and making sure that we don't have any paired spins of the same spin. So we do one up, one down in the lowest energy level, which is what we have here. Oh, my notebook closed. Okay, and we're back. So what molecular orbital theory tells us is that a bonding interaction here between the chlorine and the hydrogen, here's the chlorine, will look like this, where we have a p orbital. Let's see, we'll do this in blue and orange. So we have a p orbital, two lobes similar size, and we also have a hydrogen, and its phase must be the same phase as our p orbital that the chlorine is using in order to make a bonding interaction. And while we have this low energy state here, there's also a much higher energy state that's possible, but is a little confusing because in fact, it's not a bonding state. It's called an antibonding state. And that is made up of, again, here's our p orbital for our chlorine atom. But the hydrogen is now in an opposite phase as the chlorine. And so there's no overlap between the two. And because of that, this is not bonding because you have to have electron sharing to be bonding. And this is called an antibonding molecular orbital. And in fact, this yellow line I've just drawn is called a node. A node is an area of space where there's no electron density. It's like a big wall and it's a very high energy. That's why this state is such high in energy because the sheer energy in making that node between the two atoms. So this is what would happen in a molecular orbital theory explanation of bonding. And just a fun little aside, this molecular orbital here is the highest energy level that has electrons. In our drawing, there are only two, but it's the only energy level with electrons. So by default, it is also the highest energy molecular orbital. And in molecular orbital theory, we call this the highest, the highest occupied molecular orbital. And conversely, the high energy state up here, this one is the lowest unoccupied molecular orbital. Molecular orbital called the LUMO. So in molecular orbital theory, you have the HOMO and the LUMO, and those are what drive chemical reactivity in a molecule. So read chapter 1.8 and get some of that information for yourself. Hopefully my explanation will help you make sense of it.